Today we'll talk about the stability of partial differential equations, which is such an exciting subject that I usually don't have time to cover in my undergraduate version of this class, but now is the time to cover it. Suppose we have the 1D heat equation in a geometry where I have x pointing from here to the right, from 0 all the way to a length equal to L. I have Dirichlet boundary conditions where the temperature is fixed at 0 on both ends of this material. The material is laterally insulated, therefore there is no variation along the y direction. So it's a 1D heat equation, which is shown right here. And through my other lectures, you know the solution to this equation with Dirichlet boundary conditions. It looks something like the following. We have a bunch of summations over indices going from 0 all the way to infinity of some coefficients or weights a sub n times an exponential decaying function shown here. And lastly, we have sines and cosines. In this particular case, we have Dirichlet boundary conditions, so only the sine term stays. That comes from a direct result of the boundary condition on the left-hand side. Now, the boundary condition on the right-hand side at x equal to L gave us the eigenvalues, n pi over L, here and here. Now, the final constant of integration, a sub n, we obtained from an initial condition. So suppose in this problem we're given an initial condition that the temperature profile inside this material is a known function of x. So at time t equals 0, the temperature profile looks like this, and you're given that function f of x. Now, we can use the initial condition to obtain the final constant of integration, and we use orthogonality to obtain what that is. It looks something like the following. Just like that. So we have the coefficients a sub n, which is equal to this integral over here. So given some initial condition, f of x, we can exactly evaluate this integral. This will give you some number, because you're integrating over all x's from 0 to L, and L is some number, the length of your domain. And therefore, this integral just gives you a number. 5, pi, 10 over 4, pi over 2, some number. This goes into each of these weights, and that tells you how much of the magnitude of each mode you take. I often talk about piano keys. So A440 is one particular mode, one frequency that's contained inside the sine function. You want to know how strongly you press down on the key. How strongly you press down on the key is the magnitude of that particular key. That is equal to a sub n. Now, if you go over one key over, that is a different frequency. You can press it down again to determine how much you have to press it. That's a different a sub n. So you sequentially obtain each weight for different frequencies. So now we've built up our function, and this is our solution for this 1D heat equation. And I wanted to show you physically what this looks like. So if we have some function f of x, how would this decay? So let's go over to the screen and look at the solution to the time decaying solution to the 1D heat equation. So what I have here is a ChatGPT generated HTML simulator. Wow! ChatGPT has revolutionized teaching for me. In education, writing a single sentence saying, please generate an HTML simulator of the 1D heat equation. I want to be able to control the number of modes I take for n going from 0 to some upper limit, and I want to be able to change the initial condition. Boom! It created this simulator just in a minute. It's actually quite amazing. So you can change the different types of boundary conditions, so Dirichlet, Neumann, and periodic. So I'm just going to choose Dirichlet because that's what we have. You can change the thermal diffusivity alpha. You can change the domain length. I'm going to not touch those for now. You can change the number of Fourier modes and the time evolution. And finally, you can change the initial condition. So for example, if I were to change f of x is equal to x, that's what's shown here. So the teal line you see here, that's f of x is equal to x. That is the initial condition. Now, if I were to change the number of Fourier modes, right now I'm using 10 modes. So back on the board, that would be n going from 0 all the way to 10. So of course, we write the summation from n going from 0 to infinity in pen and paper, but when you actually evaluate it on a computer, you're going to cap the number of the upper bound. So what I'm showing here on the screen is when the upper bound goes to 10. So you can see that this is a Fourier series. So this purple curve that winds up and down, up and down, up and down, that is a sine curve where we've added mode 0, 1, 2, 3, 4, all the way to 10 added them together in the right weights to model the function f of x is equal to x. So back on the board, those are your weights. So I have f of x is equal to x. I evaluate this for each n. I know exactly how much coefficients to take. If I add them together, I get the solution that you see over here on the board. So that is the up and down motion of the purple curve. If I were to increase the number of modes, for example, to 29, you can see that the function approximates the f of x is equal to x much better. Goes straight through the curve until the boundaries. And like I said in my previous lectures, the boundaries are a little bit tricky because I have Dirichlet boundary conditions and I have signs trying to approximate an initial condition where the value at x equal to L does not go to 0. So the initial condition is a linearly ramping up temperature profile, and at the bounds, it is not equal to 0. But sign's going to make it go to 0. And therefore, the more modes I take, you would think that the solution gets better and better, and it does. It does get better, right? So if I were to increase the number of modes, you can see, so now I have what, 200 modes. Wow, you can really see that this is a straight line. It's got wobbles here and there, but look at the boundary. Over here, the overshoot is still there. And the reason why it's there is because it's saying, I'm gonna go as close as possible to f of x is equal to x, but right at the boundary, whoa, I have to go all the way down to 0. Because a sine function has to go to 0 and it's pinned at 0 at x equal to L. And therefore it's bound to go to 0, but it wants to get as close as possible to f of x is equal to x. Okay? And that causes an overshoot called the Gibbs phenomenon, or the Gibbs overshoot. And this ringing will not go away even if you increase the number of modes all the way to infinity. So this summation becomes exact as the upper bound goes to infinity. And that is true. So the Fourier series will get better and better and better approximating the solution as you add more terms. But it's converging like the 2 norm, which is saying it's converging over the integral of this entire curve. It's taking the mean squared error of the original curve and the Fourier approximation, and it's squaring it. So if I go here, you can really see the deviation between the green and the purple. It's squaring that error, and it's trying to minimize that error. That's a 2 norm. So it is indeed minimizing that. If I increase the number of Fourier modes, it is going down, except at the boundary. So how it reconciles this is that as the number of modes go higher and higher and higher, this width, which is along x, gets smaller and smaller and smaller. The ringing stays, but the width gets smaller and smaller, and it gets pushed all the way to the boundary. And therefore, as n goes out to infinity, it does indeed match the solution exactly. Anyways, that's just the initial condition. Now, if I were to go down to maybe say 20 modes or so, 21 modes, and I'm going to press play, and you're going to see the decay. Play. You're going to see the solution to the 1D heat equation. So the green curve is the initial condition. The purple is in real time. So let's reset that again. So now I'm going to maybe choose a different mode. I'll go to mode of 47. So the initial condition is better approximated. And I'm going to press play. Okay? That's just the 1D heat equation. And you can do other things. Let's change this to x cubed. Okay, here we go. So this is x cubed shown in green, and this purple approximation is the Fourier series. Press play, and it just diffuses out. Okay. This is really cool. I really like this little simulator it made for me. Let's suppose I reset it and give it sine pi. Fine, let's just use the default version. So sine pi x. That's the initial condition. In that particular case, even if I increase the Fourier modes, nothing changes. Why? It doesn't change because I have only a single mode present. It's a delta function at n equal to 1. So it only needs to pick out that one frequency. It's just one key on the piano. Every other mode is not necessary. Therefore, it doesn't matter how many modes I take. It only activates one of them. So if I press play, it just goes down. Heat diffuses out the boundaries. And at long times, it goes to an equilibrium solution where the temperature is 0 all the way across. OK, so far so good. This is all review material. So what you found is that for every single n you put in, the solution will decay. And if you look at the structure of this temperature profile, ignoring the summation for the moment, if you look at this, you have an exponential decaying function times a sine. sines are waves. So fundamentally what it's saying is I'm going to put in a wave, and for that particular wave, I'm going to see if it decays or grows or what happens to that wave. Let's consider the following. Right here. So I've written the temperature profile as some exponential function that depends on time, e to the omega t, times another exponential function, e to the ikx. Now, you know from Euler's formula that e to the ikx can be written as sines and cosines. Cosine kx plus I sine kx. So fundamentally, e to the ikx is just another way of writing sine n pi x over L. So this form has the structure, mathematical structure of what we just found using separation of variables. Now, if I were to plug in this form, or before that, physically, what this represents is the following. What we are saying fundamentally is asking the following question. If I were to pick a particular k, and k is the wave number, it's the mode, what frequency you're taking. I have some wave, given a wave, what does it do in time? Does that wave grow? Does that wave decay? What happens to that wave? So I'd like to change your mindset of how you think about separation of variables solution in this way. Waves. The entire world is made up of waves. We want to know what happens to those waves in time. That is what this structure is posing. Now, I'm going to add the exponents together because the product of exponentials, you can do that. I can rewrite it like the following. E raised to the omega t plus ikx. Now I'll get into what omega is in just a little bit, but first k. K, like I said, is called the wave number. In 1D, it's called a wave number. In 2D or beyond, it's called a wave vector because it could have multiple components in different dimensions. But for this particular case, it is just equal to n pi over L. So this is just the eigenvalue. This is n pi over L that you obtain from one of the boundary conditions. Boundary condition on the right-hand side. It's called a wave number. So generically, we can write down this family of solutions in this following way. So let's do something. Let's take this solution, e to the omega t plus ikx, plug it into the original heat equation, assuming you didn't know the separation of variables technique, and let's see what happens to the relationship of omega and k. So all I've done here is to take this guessed form of the generic solution to this PDE, plug this into this 1D heat equation. So left-hand side, partial temperature, partial time. All we get is an omega to pop outside because the derivative of an exponential is just the thing in the exponential popping outside. So omega times this thing. The right-hand side is alpha times the second derivative with respect to position, x. All we do there is we have an ik that pops outside twice because we're taking two derivatives. So ik squared e to the omega t plus ikx. Now, I squared is equal to -1. I is the imaginary unit. And therefore, that term is just equal to -k squared. Furthermore, the exponential term cancels on both sides, and we get a relationship between omega, this prefactor in front of the exponential in time, and k. And for this particular case, it just looks like that. Omega is equal to -alpha. Alpha, again, is a thermal diffusivity. It tells you how conductive the material is to heat and energy transport. Times k, which is the wave number, that's the frequency, squared. All right. So if I were to plot this thing, it will look like an inverse parabola. Just like that. So you find that the omega is an inverse parabola, always negative because alpha is positive, and k squared is also just going down. Okay, so what does this mean? This means that if you were to plug in omega is equal to -alpha k squared into this expression, you get something exactly like what we've obtained in separation of variables, right? Right here, e to the negative, this is omega. Omega times t. Alpha, k, which is the wave number, n pi over L squared times time. And the exponential ikx is just sines and cosines. So this solution just verified what we obtained with separation of variables. Now, I wanted to, again, shift our mind in thinking about interpreting this. I have a wave. I'm putting in a wave of a particular k. This tells me how quickly it grows or dampens in time. So when I choose a k, I go to some value, I have some value of k. This value of omega tells me how quickly that term, in this case, dampens. Because e to the negative alpha k squared is a dampening term. It will go down. So given a wave, these waves should dampen exponentially quickly. Exponentially quickly as alpha k squared. Let me show you that. Going over to the screen. Okay, right here what I have is another simulator which I generated in a single line, once again using large language model. What I have here is a solution to what we just found with the heat equation, but we're putting in there specific modes. So for example, what I have here is an ability to change the domain length, the diffusivity, the thermal diffusivity alpha, number of grid points meshing, that's a numerical thing, and the number of modes. So for example, I can change this to mode of 3. So this is doing sine 3 pi x over L, and you can see that it goes up and down 3 times. So that's a mode of 3. Okay? And k, once again, is just 3 pi over L in this particular case. And I can also change the amplitude of those waves. I'm not going to really bother with that now, and also the time step of the integration. Now, what I'm going to show you now is I've initialized this system with a single mode. So once again, going back to the board, I've put in a particular wave. I've put in a sine of 3. I've put in a wave, and I'm going to let the system go. And we're going to see what's going to happen to that wave as a function of time. That's what omega represents. So let's see what happens. So as I press start, those waves go away. They dampen exponentially quickly. And that's expected because over here on the board we derived that. We said that omega is equal to negative alpha k squared. So if k is equal to 3 pi over L, yeah, that's just going to be a large negative number. And omega, a large negative number, e to the large negative number times t, will just go down in time. So apparently what we found is that if you give it a sine of 3, it's going to dampen exponentially quickly. That's what this structure tells us. Let's try something else. Going back to the screen again, let's reset this. And I'm going to try something like 8 modes. So this is a higher frequency, higher pitch, because there's more ups and downs inside our domain. So now, if our formula is correct, omega scales as k squared. So if my frequency goes up, it should dampen faster. And it's go faster and faster and faster as k squared. So here is k of 8. I'm going to click start. If you must blink, do it now, because the process is really fast. Are you ready? Go. Okay, maybe you missed it. Let me just play it again. I click it, immediately it dampens. Reset. Go. It's really fast. Again, comparison, let's go to lower mode. You could already see it's slower. Mode of 2, that's really slow. Look at that. Mode of 1, it's decaying very slowly. A little faster, even faster, much faster. It's scaling as k squared. Okay? That's really cool. So fundamentally, the heat equation is just a wave and seeing what happens to the wave. And since we can build any function with waves, that's fundamentally all we are doing. You're putting in a test wave and seeing what happens to that test wave. So far, so good. Now, let's do something a little bit different. Suppose you're an amazing engineer, and many of you are. You're going to go out there and do some amazing things for science and engineering. Suppose that you're able to make a material with a negative viscosity or negative thermal conductivity. You know, in Japan, they have these amazing trains that they're building right now, and there's a pilot station already present where they're putting niobium, titanium alloys, tanking liquid helium inside the trains, putting liquid nitrogen all along the railroad tracks so that it can have magnetic capabilities with very minimal friction. It's going down to like sub 4 Kelvin. It's a couple of kelvins, and it's extremely low temperatures because the resistivity of the magnets go down as a function of temperature. So that would be an example of a material that is on its route towards superfluidity or superconductivity as the temperature becomes lower and lower and lower. That's a very unique material that we're taking advantage of. You want low friction because you want the trains to go without experiencing friction with the ground. Okay, so anyway, suppose you're able to create an amazing material at room temperature with superconductivity or superfluidity, negative viscosity, negative diffusion coefficient properties. In that particular case, what you have is this alpha to be a negative number. So I'm just going to explicitly put a negative outside. So now what? I have a 1D heat equation with a negative diffusivity. What happens now? Well, we can still try out this form of exponential to the omega times t plus ikx. You plug it into the PDE, everything stays the same except a negative sign that appears right here. So the only difference is you have omega is equal to positive alpha k squared. That's the only difference. So we can plot the same curve. It looks like this. These types of plots are called dispersion relations, when you have a relationship between omega, the growth rate, and the frequency, or the modes, dispersion relation. So now in this particular case, if you have a negative diffusivity, the dispersion relation is a positive parabola going up. Well, this looks really, really bad, because when you're positively growing up, then your exponential term, the omega, is also a positive number in time. So if I were to send in a wave, I send in this wave right here. This tells me that I'm going to explode as a function of time. That wave is just going to keep growing larger and larger and larger as a function of time. So this wave that we have right here will just keep growing. Growing in time. Just like that. So the initial curve that we had in blue will just get bigger and bigger and bigger as a function of time, exponentially in time, that scales as alpha k squared. So let's go back to the screen again, because we can actually simulate that right here. So this diffusivity, I can just turn it into a negative number. Here we go. So all you've done is to create a negative diffusion material, if such a thing exists. And I initialize it with maybe a smaller mode, for example, I don't know, mode of 4, and I'm going to let it go. It just explodes. Okay? That little wobbly thing are just numerical instabilities. You can see when I click very quickly, you can see over on the y-axis that it's like hovering at e to the positive 300 or something. It's just craziness. So it's just numerically exploding all the way out to infinity. At the end, you're just getting NaN, not a numbers. So that is a sign that whatever wave we put in, all of those waves will just explode. And this is true for any term. So I can go at mode of 13, start, it just explodes. Okay? So that's consistent with our intuition. We have this exponential form, it's positive, it's just going to diverge as a function of time. Okay. So now you're starting to see the change in the way we're thinking about this equation. It's really a wave, and we're seeing what happens to that wave. So what we would say is that the normal heat equation is stable for all modes k. Because for any wave that you put in there, a test wave, they're always going to dampen. It's going to dampen more quickly, higher frequency, but it's always stable. It's unconditionally stable. In contrast, when we have a negative diffusion coefficient, then we have an unstable problem for all modes. And you just saw that for whatever mode we put in there, it's going to diverge exponentially quickly. That is unstable. All right. We're starting to get a little bit of sense of how these waves behave as a function of time. Let's do something interesting. Suppose it wasn't just a Laplacian term. Suppose we have an equation like the following. Just like that. So we're going to keep the negative diffusion coefficient right here. I've removed the alpha just out of convenience. I've just set it to be equal to 1. That's not necessary, but it just makes the discussion a little bit more clear. So I have a negative diffusion, still present, but I've added what's called a biharmonic term. It's a fourth order derivative with respect to position. Have you ever solved the fourth order term before? Mechanical engineers solve this all the time because bending, beam bending and buckling is a fourth order derivative. So it does come up in science and engineering pretty frequently. Here's one example of that. And actually, Fourier's relationship, which related the heat flux to gradients in temperature, is just a linear approximation. If you expand the Taylor expansion a little bit further on, so you don't clip it off at gradients in temperature only, but keep higher order gradients present, you're going to get higher order derivatives over on the right-hand side. The energy balance is a law. That is a fundamental equation of physics. But you need a constitutive relation to close that equation. That relates the heat flux to the temperature. All along, when you're removing all the other higher order terms and just keep this first Laplacian term only, that is an approximation. So it turns out fourth order term can exist. Sixth order term, eighth order terms could technically exist. That's just a more accurate version of the heat equation. In any case, suppose you have this equation. It seems like it's still unstable because you have this negative diffusivity, but you have this other term. How does that affect stability? So question number one is it stable or unstable? So the fundamental question is this equation stable or unstable? If I were to put in a wave of a particular frequency, does that wave grow in time or does it dampen in time? Well, we could figure that out by using the same trick. So we're going to let the temperature equal to this form. You put in a wave, e to the ikx, multiply it with an exponential, omega t, see what happens to that wave. We're going to plug in this expression into this modified PDE. And at this stage, you can kind of do these things in your head. So left-hand side spits out an omega. Same thing. This first term on the right, it just gives you positive alpha k squared. That has not changed. This term right here, fourth order derivative with respect to x. Therefore, I'm going to ik to the fourth power to pop outside. Now, I to the fourth power is negative 1 squared, just positive 1. So I get k to the fourth to pop outside. So I get negative k to the fourth. Okay? So all we have that's different here is we have this. The growth rate omega for this PDE is k squared minus k to the fourth. What does this look like? Let's plot it. So I'm plotting k squared minus k to the fourth. For small k, does it go up or does it go down? If k were to be a small number, 0.1. 0.1 squared is 0.01. 0.1 to the fourth power is 10 to the minus 4. So that's small, k squared is going to win out. If k squared is going to win out for small k, it's going to grow positively. So it's going to go up, like a parabola, okay? Because this one's going to win out for small k. But at very, very large k equal to 10. 100 minus 10 to the 4. So now negative k to the fourth is going to win at large k. So that means that for very large k, it's going to be a large negative number. So this has to turn over, and it's going to look like that. So it's got some regions that are positive, similar to how this one was positive, but it's got some regions that are negative, like the original heat equation where it was always negative. Where's the crossover? k equal to 1. So everything up here is unstable. Everything down here is stable. And this means that if I were to give it a wave for k less than 1, those waves are going to grow because you can clearly see it. It's in the unstable regime. It's going to keep growing. But if I seed it with a high frequency oscillation for k larger than 1, those waves are going to dampen, man. They're going to go away. So it's both stable and unstable, depending on which wave or what kind of wave you initialize it with. So let's see what this looks like. Let's go over to the screen where, once again, here is a large language model generated HTML simulator. This one is actually solving this PDE. So partial u partial time is equal to negative Laplacian minus a biharmonic. So that is literally the PDE that we're solving. Okay, so we can do in this simulator is change the number of modes. So for example, this is n of 5. And for n of 5, this gives us a k equal to 2. So that is just taking 5 times pi divided by L. Okay, that is equal to 2. And you can adjust the domain sizes and grid points over here, but you don't need to focus so much on the details of these numbers here. It's the point is, for a mode number n of 5, we get a k value equal to 2. So going back to the board again, for k of equal to 2, that's way out here. So you would expect those modes to be stable. So let's see what happens. I'm going to play this movie. So here's the wave of n equal to 5 going up and up. So that's a high frequency mode. When I play it, what's going to happen is that those modes all decay. Okay, let's see that again. It just dampens out. Okay, that makes sense. And that's happening because the biharmonic term is winning out. Right? Fundamentally, that's what's happening. This negative fourth order derivative with respect to position is just winning out. It's like, I'm in charge. I'm going to stabilize all of these waves and make it go all the way to 0. But if I were to, for example, add another mode, let's see here. I'm going to add another mode of n equal to 2. I'm going to change the amplitude a little bit. So I'm going to change the amplitude to 1. So this is a mode of 2, which the k value is equal to 0.8. So now, going back to the board again here, what we've done is seeded this initial condition with one mode at k equal to 2, so that's n of 5, and another mode at n equal to 2, which is k equal to 0.8. So it is seeded with one value right around here, and another value all the way out here at k equal to 2. So this is a superposition of two waves. So going to the screen, you literally see that. This is a superposition of two waves. One wave, mode of 5, one wave, mode of 2. And you can kind of already see that. You can see there's two kind of big waves that were added together that creates this overall function. So now what we're going to do is to click play, and you can maybe picture what's going to happen. So what we expect is the high frequency mode is going to stabilize and dampen out, and the unstable one, the large lazy oscillation, those will stay. Let's play this. There it is. You just saw the high frequency mode dampen away. Once again. The high frequency mode goes away, and the long, lazy oscillation, the large wavelength mode ends up just staying. So this will be analogous to like if you're inside a room and you have a long, lazy, slow frequency oscillation. It would be like I have 0 degrees here, 1, 2, 3, 10 degrees all the way out here, and then that would be a long variation in temperature. That would be like a sine wave that goes slowly up and down. Those modes are going to diverge. But all the small little microscopic, small little temperature fluctuations, which is like 0, 100, 0, 100, 0, 100, 0, 100. Those variations in temperature, those would be high frequency. Those are way outside k bigger than 1. Those are going to dampen out exponentially quickly. So what we're going to see by eye macroscopically is the large lazy oscillations win out. And that's what you're seeing over on the screen. The reason why you're not seeing these get bigger and bigger and bigger is because in this HTML simulator, presumably, the y-axis is being renormalized. So it's actively growing and growing and growing, but the y-axis is being scaled, and therefore it's just, you're not seeing the growth of it, but it is diverging and it's exploding. Okay. So, really, really cool system where if I were to have two waves, one long and lazy, the other one high frequency. The high frequency ones will quickly dampen away, whereas the long lazy ones are unstable. And the dividing line between them is k equal to 1. That's what this PDE tells us. Really, really cool. So now you're starting to really see this equation fundamentally differently. It's not that old separation of variables way of looking at it. It's looking at it as a wave. You give it a wave, what happens to that wave? And you can tell a lot about the stability of PDEs, which is incredibly important. All right, let's end this lecture by doing a really cool thing. Let's talk about nonlinearities. Suppose that I have this equation. I add one more term to it. I add a term that is negative t times the spatial derivative of t, partial t, partial x. Now the world has changed because we have a nonlinear partial differential equations. All of these terms in blue, those are linear terms. This one is a nonlinearity because we have t times its derivative. That is a nonlinear term. Is this equation stable or unstable? Or what does it even look like? What happens when you put nonlinear terms inside of a partial differential equation? Well, let's first think about what happens to a wave that you insert inside this PDE. In particular, let's focus on what happens to this nonlinear term when it takes in a wave. We already know what the blue terms do because we just built that up one term after another. So you know exactly what the blue terms do. Those are the linear terms. This new term, nonlinear term, what does it do when it takes a wave? Okay, so what I've done here is to take this nonlinear term, put in this exponential form for the temperature. So that's just t, that's the linear term, t, times this other derivative of the temperature with respect to position. So I take the spatial derivative of this exponential form, I pop out an ik, similar to how we calculate over here, we get an ik to pop outside, and it looks something like this. This is a product, right? It's a nonlinear term. And if you simplify this, it looks like this. All right, so I just simplified the exponentials and added them together. But I want you to focus on this term right here, e to the I times 2k times x. Something crazy just happened because this one fundamentally looks like sine 2kx cosine 2kx. But we inputted a sine 1kx. So our input, the temperature, into this term was a sine 1kx. So we put in a sine kx term. But through the nonlinear terms, this input turned into an output, which is a higher frequency. It got upgraded to a 2kx. And that's really interesting. What that is saying is I'm going to send in this wave of k equal to 10 oscillations. I'm going to send in this wave into this equation, and then out came a 20 wave thing after this nonlinear term. So that's what happened. I sent in a particular wave, but the nonlinear term turned it into a much higher frequency wave. That's a new thing. That hasn't happened. All of these linear terms that I'm showing here in blue, if you send in one wave, the same frequency wave is going to come back. It's going to be attenuated or grow, or the amplitude is going to change because the amplitude depends on e to the omega t. So that will change. The amplitude will go up and down. But the fundamental frequency, what frequency wave you sent in, will always come back. That's what it means to be linear. You send in one wave, the same wave comes back with a different amplitude. But this nonlinear term is saying, I'm going to send in one wave, and it's going to come back and give me a completely different frequency. This is called mode coupling. Mode coupling. It's the shuffling of frequencies from one to another. And nonlinear terms have this property. Linear terms cannot mode couple. And it's coupling mode. The kind of name is nice, right? You have modes and they're coupling and they're shuffling amongst each other. And nonlinear terms like this can do that. So, the plot thickens. We were building one thing one at a time, and we felt like we understand stability, there's a critical K, and you can do all these things. But this nonlinear term all of a sudden just kind of changes the picture. So, physically, what would happen to this equation? We already know what's going to happen to linear terms. For the linear terms, what we already know is that the long, lazy oscillations will grow in time. So this term, the negative viscosity term, the Laplacian, is going to grow. But the high frequency ones are going to die. That's what these two terms are saying. Now the nonlinear term is very interesting. It's going to say, give me a wave, and I'm going to shuffle it to a higher frequency. And when would this term get bigger and bigger? Let's draw some curves. So, step one. This negative viscosity term will grow and grow and grow for small k. Let me graph what that would look like. So if I were to have a wave that looks like this, so that's a relatively long, lazy oscillation. Those will start to grow. So that wave, due to this negative Laplacian term, is going to grow in amplitude, just like you saw earlier. So this wave will grow bigger and bigger. So this is the progression of time. Okay? But look what happens. As the amplitude gets bigger and bigger and bigger, so the temperature profile is getting larger and larger and larger, the slope of these terms are also getting bigger because you're taking the difference between two points that are getting bigger and bigger and bigger and farther separated over the same distance, and therefore the slope of that is getting larger and larger and larger. And their absolute magnitudes are also getting larger. That means that this term is going to become more and more and more important as these amplitudes grow. When it's early time, this term isn't activated because t is small, the derivative of t is also small. So you're multiplying two small numbers. This looks like epsilon squared. This term looks like epsilon, but it's growing, 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 growing. As it grows, now this is no longer epsilon. These are large numbers, and the slope is also a large number. So you're multiplying two very large numbers, and now your nonlinear term kicks in. It's saying, sweet, I'm in control now. I'm going to take this wave and fracture it into a higher frequency. So it's going to take this wave, and it's going to fracture it into a higher frequency mode. Because that's what mode coupling does. It takes in one wave, it fractures it into a higher frequency thing. So that's step two. So step two is now that this negative viscosity has upped the magnitudes of the temperature and the slopes, this nonlinear term kicks in and shuffles the modes. That's this right here. It takes in one frequency, pops out a higher frequency. Mode coupling, shuffling of the modes. But as it continues to do that, as it continues to fracture more and more of these to higher and higher frequencies, what happens? Now we're going to drive our k to larger and larger values and higher frequencies because eventually the nonlinear term is going to spit out terms that look like this. Well, that's a high frequency mode. That's sine of 100x. Then this term comes to the rescue, the stabilizing biharmonic. So step three is the biharmonic term stabilizes the high frequency mode. So it's a cascade of reactions that happens. First, I have an epsilon fluctuation. The long, lazy oscillations start to grow. As it grows, the nonlinear term starts to shuffle the modes together. It's going to take in, ooh, nice, sine x. I'm going to give it sine 2x, sine 4x, sine 8x, sine 20x, sine 40x. It's going to start to shuffle these modes to higher and higher frequency. But then as it gets passed on, this third step, the biharmonic, says, look, this high frequency thing, I got it. I'm going to completely stabilize it. That's what this term does. So it's a cascade of events that happen where each term just does their job. And this nonlinear term, the shuffling of modes, is the thing that passes it from the small k to the large k. Unstable, stable. Shuffles it from left to right, go, 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 go. So this plot, I'm plotting it as a function of x. Right, I'm plotting the temperature profile. Right, those are temperatures. But if you were to replot what I just showed you in a Fourier plot as a function of the wave number, it will look like this. So now we have the temperature as a function of the mode number. It's a different way of thinking about what we just talked about. So for small k, what we have is unstable growth due to the negative viscosity. Therefore, these modes over here will keep growing with time. That's step one. Step one is these small k's will tend to grow because it's unstable. The temperature is going to go up, 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 up. But as that happens, the nonlinear term kicks in, because the temperature is going up and the derivative is going up. Therefore, a big number times another big number is a very big number. So this term starts to control and says, oh, thank you. All I'm going to do is take your terms and shuffle it, pass it over to the right. So this cascade of handoff from small modes to high modes is step two, shuffling, mode coupling. But for large k, it's stabilizing because the biharmonic dampens it out. That's step three. Do you see this amazing cascade of reactions that are happening? Growth, 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 pass, 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 stable, 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 grow, 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 pass, 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 stable. This is the physics of this equation. It is a remarkable differential equation. Let me show you what it looks like. So what we have here is a HTML simulator that solves the equation we just talked about. Now, what I'm going to do is show you this in a couple of different ways. First, I'm going to seed the solution at a low k, which means I'm going to put in there an initial temperature profile. This is the function that you want, so this is temperature in our case, as a function of position. So this is in real space. Temperature starts high, goes down, and then goes back up. That is a long, lazy oscillation. I'm putting a low k to initialize. So back on the board, that would be like I'm giving it a small little peak for small k. I'm giving it a low k. And you can tell from the screen here that the magnitude of these perturbations are small. It's 0.04. So that's a small little seed that I'm giving it. Now, over on the right, what we're plotting here is the amplitude of that as a function of the mode number. So that is a function of k, effectively. So you can see here, there's this large peak at n equal to 1, I guess, 1 or so. So then that means that it's giving an initial condition spiked at n of 1. So that's sine 1 pi x over L. And you can see all the other values are equal to 0 because it's just a low k. There's no other sine frequencies present. Now, I'm going to let the simulation run. And if we're all correct, if the diagram over here on the board, where now if I seed it with a low k, it's going to go up, 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 pass, 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 stable, that should happen. We should see that in the simulator. Let's see what happens. Start. So you can see already it's growing, right? 0.05. These points are growing. It's getting larger and larger. And you can see, look, it's activating higher modes. Mode coupling is kicking in. These small modes are getting passed on, passed on, passed on. Look, the interface is forming, and these gradients are steep. The nonlinear terms are passing more modes. But over at these high modes, it's stabilizing. And now we have a fully developed solution to this nonlinear fourth order differential equation. It is an amazing PDE. Look at this thing. Look how beautiful this is. So you have these chaotic structures. We have these oscillations happening. And every once in a while, these things will merge and do crazy dynamics. You can really see that over here, now it's achieved some kind of steady state. So let me show you again, reset that, and start something different. So this time, I'm going to seed it at high K. So let me see here. I'm going to seed it in at high K, take a step. Here we go. So I've cleaned out the solution again. Now what I've done is to seed it with a high K instead. Okay? So now you can see this is a high frequency oscillation. I've put that in there. And over here, it looks like there's a couple of modes. So there's a mode of, I don't know, is that like n of 20? So that's a sine of 20 pi x over L. And then another one at around 40, another one around 60. Okay, so just high frequency modes that are put in as an initial condition. And you can see all the other modes are 0. So it's just a high frequency test wave that we put in there. And if I were to click start, what happens? It's just stabilizing. All the waves went away to 0, and you can see the time is still running, but the temperature went all the way to 0. I'm going to restart this, and the same thing will happen. There we go. Once again, boom, goes away. So now back up to the board, that kind of makes sense because all we've done is to stabilize the seed all the way out here. So if you're all the way out here, all it will do is the biharmonic stabilizing term will just dampen out to 0 and nothing happens. So it's really the coupling of everything. It's the coupling of all three terms talking to each other that gives rise to this really cool phenomenon. So let me just show you one more time using a different initial condition. So what I'm going to do is to just give it a seed and add a little bit of noise. So this button adds noise. So what I've done is to seeded it with low frequency somewhat, I guess, a couple of frequencies at low modes, and then also gave it a little bit of microscopic noise that you can't see. Effectively, what we've done is to add temperature. You're injecting thermal temperature into the initial condition. Because you can look and see that this partial differential equation does not have a noise term. There's no stochastic noise. This is a deterministic partial differential equation. The temperature, it gets seeded in at the initial condition. So at the initial condition, I'm going to put in some temperature that gives it microscopic noise, and that's all you need for the system to deterministically take it away. So let's start it, and you can see what happens. Small modes grow. They're growing, growing, growing. Nonlinear term picks up. So now we're in the shuffling of modes situation, and as it keeps growing, now the positive stabilizing biharmonic term is preventing this system from completely exploding. So cool. So amazing to see this. Look at these interfaces. You can see these waves and shocks happening. And these waves and shocks happen because of the nonlinear term. It's taking waves and moving them, propagating from one location to another. It's shuffling modes. Nonlinearity is an amazing thing in physics and science and engineering. And over here, you can see all the effects taking place all at once. These small modes want to keep growing, but they're not growing because the nonlinear term keeps shuffling it to higher and higher modes. And those higher and higher modes are being dampened out, going to 0, because of the positive stabilizing biharmonic term. So this is a system where it is linearly unstable, but globally bounded. It is an amazing system. I feel like I can look at the simulation all day long. By the way, this equation is very commonly used to model interfacial phenomena like flame propagation or catalysis happening at interfaces. Doesn't it kind of look like a fluid interface or a catalytic interface along a surface? You have some kind of phase here below the curve and another phase above the curve, and you have some jagged interface. And there's some kind of chemical reaction happening along the interface that then reacts and consumes and grows. this is a very common model that people use to describe that kind of phenomena. So it's not just a example I just made up. It's a very famous equation that people use to model physical systems in reality. Okay, I can watch this all day. A lot of things just happened, and I hope you got a sense of how amazing nonlinear terms are to a differential equation. Before I included this nonlinear term, we just had the two linear terms. That was that was already kind of interesting, but not super interesting, because all that did was create a divide between stable and unstable. K of 1 was the dividing thing. Above, stable, below, unstable. Inclusion of the nonlinear term made them talk to each other. That's what it did. This communication between these two sides, straddling k equals 1, is precisely what this nonlinear term did. So this nonlinear term is called a bounded attractor. And once again, this equation is not linearly stable. And you saw that, because if I were to take away this term and just consider the linear terms only, it was unstable, right? For small k, it was growing, it was unstable. Sure, the high k was stable, but if you have any mode that's unstable, it's unstable. It was linearly unstable. But when you add the nonlinear terms, it became globally bounded. It's still locally unstable because the small frequency is growing, but because the nonlinear term is shuffling it to a stable region, it's globally bounded, and that's why we get a steady state where the temperature doesn't explode. You saw that simulator image, it never exploded out to infinity. It was bounded, right? It was shuffling, moving, but it was always bounded between a value of around -2 to +2. And that's solely because of this nonlinear term. This equation is so famous that it has a proper name to it. It's called the Kuramoto-Sivashinsky equation, KS equation. That's what we just built up from scratch, all the way from the heat equation over to this very complicated phenomenon. Now, Kuramoto and Sivashinsky are amazing scientists. Kuramoto was studying reaction diffusion systems and catalysis, like I alluded to earlier, to think about what happens at interfaces. And Kuramoto is actually an amazing nonlinear physicist, dynamicist. He's at Kyoto University, and he's actually very famous for developing what's called the Kuramoto oscillator. Maybe you've seen this really famous video or phenomena where you take a bunch of oscillators and connect them together on rolling tables. They'll all start to synchronize. You take a metronome, like tick, 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 those metronomes that you use to synchronize your music. Those metronomes, even if they're out of sync, if you take a bunch of them, they'll start to sync up together. That's a Kuramoto oscillator. So Kuramoto sensei, has done a lot of stuff. In fact, when I was at Kyoto University, I was walking along the hallways before a seminar, and I was walking with my host, and I saw this nameplate that said Kuramoto. And I was like, wait. あれ、Kuramoto sensei no office desu ka? Is that Kuramoto sensei's office? I really love a lot of the things he's put out for all of us to appreciate and study. So Kuramoto oscillator, Kuramoto-Sivashinsky equation, nonlinear dynamics is such a cool concept. And very interesting connection that Kuramoto's PhD advisor was Mori. Mori of the Mori projection operator technique, of Mori-Zwanzig of 1965. It's a very important Mori-Zwanzig formalism that's used in course screening in statistical physics. So there's a long legacy of really amazing physics coming out of Kyoto University, I guess all the way back from Yukawa, the first Nobel Prize winner from Japan, but there's this long legacy that continues. And it's still continuing today. Kuramoto's student is currently there doing amazing physics. So I just really love teaching this example for so many different reasons. Sivashinsky is also an amazing scientist. He's a Russian-Israeli applied mathematician, physicist at the Weizmann Institute in Israel, one of the best places for humanities, science, and engineering. Sivashinsky was studying combustion theory, nonlinear instability of flame propagations and wrinkling fronts around the flame. And so this equation has been used to model all sorts of really, really cool dynamics. It's called the KS equation. Great. So one last thing. Have you ever seen this term before? Doesn't that look a lot like this? The Navier-Stokes equations. That's turbulence. Turbulence has that characteristic. It's V times the gradient of V. There it is. V times the slope of V. There it is. So in fluid flow, turbulence has the exact same characteristic. People often talk about an energy cascade of small frequencies to high frequencies, or high frequencies to small frequencies. That energy cascade of mode coupling is precisely due to this term. This term is the reason why large hurricanes and tornadoes over a kilometer scale can become smaller and smaller and smaller to a small little eddy happening on a micro scale that eventually dissipates and goes away. The enormous change in scale from kilometers to microns to nanometers, that's possible uniquely because of this term. Nonlinearity is one of the most amazing things in science. It's a little bit of a shame that there aren't a lot of tools to understand nonlinear terms in partial differential equations, because there are very few tools that we can use to analyze nonlinear terms. With linear equations, there's a whole host of terms. Superposition, separation of variables, all those things work. With nonlinear terms, you can't use most of them anymore. All right, I hope you enjoyed this. If you know the heat equation, separation of variables, all of this development up to nonlinearity and turbulence and coupling and everything I found amazing. I hope you enjoyed. I'll see you next time. Bye.